Hello, this is Math Jazz from Almost Cool, and today we are going to be talking about equivalence relations. So, I have the definition up on the screen of an equivalence relation. It says, R is an equivalence relation if R is reflexive, symmetric, and transitive. So, let us recall what those three things mean. So we have there we go. Reflexive means that every object A is related to itself. This is the symbol that I'll be using for related here. Or maybe that symbol. So let's A is related to A. Now, relations are kind of like equals signs. So the way that we're going to think about relations is they're not exactly equals, but equivalence relations are a lot like equals. And equivalence relations are special. They have these three properties. One is reflexivity. Two is transitivity, which means that if A is related to B, then B is related to A. And this one is called reflexivity. This one's called symmetry. And this one is called transitivity. And it says that if A is related to B and B is related to C, then A is related to C. This is called transitivity. So, if it has these three properties, then we have an equivalence relation. And equivalence relations are about as close as you can come to equality without actually being equality. So, I guess another type of relation is called an order relation. This will give us our example of a non-equivalence relation. Order relations are like the points on this number line have an order to them. These are the ones that come first on this side, and these are the ones that come later on the other side. Order relations are not equivalence relations. Because, for example, if this point is A, and this point is B, and this point is C, A comes before B. But B does not come before A. Sorry. So this fails the symmetry part of an equivalence relation. So that an order relation and an equivalence relation will never be the same. But this is an example of a relation that is not an equivalence relation. Okay, so let's give an example of an equivalence relation then. Equals is an equivalence relation. For example, if 2 plus 2 equals 4, then 4 equals 2 plus 2. See, we can switch the two sides of our equal sign, and it's still a true statement. You can't do that with a less than. 3 is less than 4. 4 is less than 3 is false. See? So this is, again, an order relation. And this is our equivalence relation. Okay, so this is the symmetry part. That's probably the easiest one to check, as we can just swap sides of an equal sign and it doesn't change anything. The next thing is, does anything Or does everything equal itself? Well, of course it does. On the other hand, like, nothing is less than itself, so order relations fail on that as well. So everything is less than or equal to itself. So if you swap this is still an order relation, but it's this one is a reflexive one, and strong inequality or strict inequality is not a reflexive order relation. Okay, and then I guess the last thing to check is transitivity. So transitivity, if A equals B and B equals C, does A equal C? Yeah, that's obviously true as well. So equals is an equivalence relation. Great. So we already know an equivalence relation. However, there are lots of these, and equals is just one of them. But they all have these similar properties, and that allows us to do a lot of things with them. So, for example, if we look at the integers, here's our symbol for the integers, and that's going to be the set of like -3, -2, -1, 0, 1, 2, and so on. You know, all of our counting numbers and their negatives and 0. Well, it turns out that we can do equivalence relations on Z of remainders when dividing by 2. So, like, for example, we call this modular arithmetic, and we call this mod 2 because we're dividing by 2 and seeing the remainder. So there are a group of numbers like -4, -2, 0, 2, 4, and so on in both directions. These are all 0 mod 2, or the even numbers. And then there's another group, -3, -1, 1, 3, and so on in both directions. These are our numbers that are 1 mod 2, or our odds. Okay, so turns out that these form an equivalence relation. So the equivalence relation is A is related to B if A mod 2 is congruent to, let's see, the way that we usually word it in class is A is congruent to B mod 2. So let's do it that way. A is congruent to B mod 2. So, and so we've been using this kind of a thing all semester so far, so we should feel very comfortable with it. But it turns out this is indeed an equivalence relation. So let's scroll down a bit. Do I not have the ability to scroll down? Okay, so we have here for all x in the integers is x congruent to x mod 2. Well, yes. And there are a few ways that we could prove this. Probably the easiest way to say is to say by the division algorithm. So that's going to be that x is equal to 2q plus r for some r that's either 0 or 1. And then, hey, look, this is our remainder, and q and r are unique by the division algorithm, so is x congruent to x? Yes, because they will have the same remainder after dividing by 2. So, yes. That's true. We are reflexive. Are we symmetric? So, that means that for all x, y, and z, if x is congruent to y mod 2, is y congruent to x mod 2? Well, yes, that's also going to be true, because x is going to equal 2q plus r for some remainder r and some quotient q, and y is going to equal 2q, well, its own q plus its own r. And so if x is congruent to y, then r equals r prime. So r prime equals r, so y is congruent to x. Okay. So that's not too hard. And I guess the last thing to check is now transitive. Like, if x is congruent to y, and y is congruent to z mod 2, then is x congruent to z mod 2? And the answer is also yes. Oops. And the reason we can do this is we get x equals 2q plus r, y equals 2q prime plus r prime, z equals 2q double prime plus r double prime. We know that r equals r prime, and r prime equals r double prime, so r equals r double prime, so x is congruent to z mod 2. Okay, that's not so bad. We just proved that we proved that equivalence mod 2, or congruence mod 2, is an equivalence relation. We could do this for any modulus, not just 2. Works just fine. So yeah, let's look at the book and see what else we're learning today in this. So here's our book. Yep. Or maybe this is the book. There we go. Okay, so that was our definition of an equivalence relation. And now we're going to define equivalence class. Okay, so an equivalence class is what it says here. It says that if A is a set and tilde is an equivalence relation, then we can define some subsets of A. Okay, so 2's the book, and 1 is the notepad, or the paint.net pad. Okay, so we have, we can define these sets. We label them with these square braces here, and they're going to be the set of all things that are related to A. So one way that we can think about these equivalence classes as kind of like pizza slices or um, or jigsaw puzzle pieces. If the set is the whole puzzle, then the equivalence classes are all of these little jigsaw pieces that are all full of well, let's say that the puzzle was printed on a printer, and so it has a bunch of little pixels on it. Okay, so all of the elements of the set are the little pixels, and each of the equivalence classes is each of the pieces, and each pixel can only be on one piece. It's on exactly one piece. When you put all the puzzle pieces together, you get the whole set back. Okay, I think that that's actually a theorem that you prove. But maybe it's not. Anyway, that is something that we do get to know, is that an equivalence relation creates equivalence classes in a set. Likewise, if you have what's called a partition, which is a complete set of equivalence classes, you can construct an equivalence relation for them. That's why we use the same word equivalence in both of these. Anyway, we have some exercises here that we'd like to take a look at. So let A be the set 1, 2, 3. R is the relation given that R. And we want to know if R is reflexive, symmetric, transitive, antisymmetric, and an equivalence relation. So, and we want to prove all of this. So let us pull up our paint.net pad. That's 2. Is that 1? That's 1. Okay. And so we have our relationship here. 1, 1 is in the relationship. 1, 2, 2. Oh, gosh. So that went by a little fast, but 1, 1. 1, 2. 2, 1. So let's look back at the book. 2, 2, 2, 3, 3, 2, and 3, 3. Here we go. So we have 2, 2, 2, 3, 3, 2, and 3, 3. Okay. So what this means is that 1 is related to 1, 1 is related to 2, 2 is related to 1, and so forth. Every one of these ordered pairs is a relation that is true. The ones that aren't in this list are not related. So for example, 1 is not related to 3 because 1, 3 is not in this list here. Okay, so with that, we want to know, is this thing symmetric, reflexive, and so on. So reflexive is the easiest to check. Is this reflexive? Yes. Why? Because every element in our set A, which was 1, 2, 3, every one of these elements is related to itself. 1's related to 1, 2's related to 2, 3's related to 3. So it is in fact reflexive. Is it symmetric? Well, to be symmetric, we need to know that every relation one way is reflected the other way. So anything that's x related to y implies that y is related to x. So 1's related to 2, and 2's related to 1. So far, so good. 2's related to 3, and 3's related to 2. So far, so good there. And none of the other ones will, like, for example, 2's related to 2. Switch the spots. Hey, look, 2's still related to 2. It doesn't change anything. So these are all good. We've checked all of the elements, so this is in fact symmetric. So, yes. Is it reflexive? Sorry, is it transitive? Well, 1 is definitely related to 2 from this, and 2 is related to 3. If we were transitive, transitive would imply 1 is related to 3. But that's not on the list. So, no, not transitive. Okay, so not transitive, and then we want antisymmetric. Okay, so antisymmetric is the one that says that if x is related to y and y is related to x, then x equals y. Is that true? Well, no. 2 is related to 3, 3 is related to 2, 2 is not 3. So no, not antisymmetric. Okay, let us go back to our book. And from our book, let's see. The next one is give an example of an equivalence relation on R give an equivalence relation R on the set 1, 2, 3, 4, 5 that has exactly 2 equivalence classes. Explicitly write out the relation R as a set of ordered pairs. Okay, so our set A is equal to 1, 2, 3, 4, 5. And we want to write out R to be an equivalence class. Well, to be an equivalence class, we need to be reflexive, so that means that everything needs to be related to itself. So let's just write those in right now. Okay, so we have those. Now, this is actually also transitive and symmetric vacuously. But it has 5 equivalence classes. We need 2. So let's start combining some things to give us some, to make our equivalence classes join together. So let's say we have like 1 is related to 2. Well, to make it symmetric, we need to have 2's related to 1 in there. Okay, so we have this so far. Now we have 4 equivalence classes. We have the equivalence class that has 1 and 2 in it, and then we have 3, 4, and 5 in their own equivalence classes. So let's combine 3 and 4. We have 3, 4, and 4, 3. Okay, so now we have the equivalence class with 1 and 2, the equivalence class with 3 and 4, and 5 is in its own equivalence class. So let's add 5 into one of the equivalence classes. Let's do 1, 5. And that means we have to add 5, 1. So now we're reflexive and symmetric, but we're no longer transitive because 1 is related to 5. And, let's see. 2 is related to 1, 1's related to 5, but 5's not related to 2. So since we have 2, 1, and 1, 5, we need 2, 5. So let's add that, 2, 5, into our relation. And then to be symmetric, we need to add 5, 2. So now we're reflexive, transitive, and symmetric, and we have the equivalence of 1, 2, and 5, and the equivalence class of 3 and 4. So here is our relation explicitly written out as ordered pairs. Okay, so let's look at our next problem. Let R be an equivalence class, an equivalence relation on the set 1, 2, 3, 4, 5. Assume 1 is related to 3 and 3 is related to 4. Given these conditions, which ordered pairs must belong to R? There are at least 11 such elements. Okay, so let us go and figure out what those 11 elements have to be. So we know that 1 is related to 3 and 3 is related to 4. I'm going to write these twiddles instead of the R's. I think they're easier to read. Okay, an equivalence relation has 1, 1 in it, 2, 2, and well, I mean an equivalence relationship on the set 1, 2, 3, 4, 5 must have every element related to itself. So here's our R equals 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Okay, we also know 1, 3 is in there, and 3, 4, because they give both of those to us. And because we're symmetric, we need to have 3, 1, and 4, 3. Let's, oops. There we go. So now we have everything related to itself, everything that's related to something else. We have the symmetric property. We don't have transitivity yet because we have 1 related to 3, 3 related to 4, but we don't have 1 related to 4. So we need to add in 1, 4. By symmetry, we have to add in 4, 1. And let's see. Now we are transitive, we are reflexive, and we are symmetric. That should be it. Let's count. They said there should be at least 11 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Great. Looks like we got them all. Now, that's not to say that this is the only equivalence relation that has 1 related to 3 and 3 related to 4. It's just saying that that any equivalence relation has to, with those properties, must have at least these relations. If we added more relations, we could still get other equivalences. So, with that, next problem. Let's take a look in our book. Okay, so let A be the same set and S be this. We want to define a relation. Okay, A is related to B if for some X and S, both A is an X and B is an X. Okay, so we have seen that R is an equivalence relation. What are the equivalence classes of R? Well, they're the ones in S. S is a partition of A, meaning that S is the collection of equivalence classes of A. So let us see that out on paper. Oops. S for select. There we go. Okay. So we have oh, we don't need this either. We have S is equal to the set of 1, 2, 3, 4, and 5. Now we know that R is defined as A is equivalent to B if there exists X in S such that A, B exist in X. So they have to be in the same set. So like 1 is related to 2 because there is a set, this set that they're both in, but 1 is not related to 3 because 1 isn't in the same set as 3. Okay, so let me make sure I copied that right. 1, 2, 3, 4, and 5. Okay, so is this or this is an equivalence relation. Let's show that it's equivalence classes. Well, let's look at the equivalence class of 1. So that's going to have 1 in it because 1 is obviously in the same element of S as itself, and then 2 is also in that set. And there's nothing else that is in that set. The equivalence of class of 2 equals the equivalence class of 1, so we're going to skip writing it. 3 is going to be 3 and 4, and 5 is going to be the set containing 5. So these are our these are the equivalence classes of the relationship R. So let's look back at our book. Okay, so we now have A is all non-zero real numbers. We're going to define a relation by A is related to B. If A times B is greater than 0, we're going to prove it's an equivalence relation. We're going to determine the equivalence classes of tilde. Okay, so that's not so bad. Back to .NET. So A is related to B if A, B is greater than 0. And we know that A and B are never equal to 0. So, well, let's see. A times A is a square of a real number, which is greater than 0, so we are reflexive. And then A times B greater than 0 means that B times A, which is equal to A times B, is still greater than 0, so this is symmetric. And then AB greater than 0 and BC greater than 0 implies what? Well, A times B greater than 0 implies either A and B are greater than 0 or A and B are less than 0. Same thing with BC greater than 0 implies B and C are greater than 0, or B and C are less than 0. So, if B is greater than 0, then A is greater than 0 and C is greater than 0, so AC is positive. Or if B is less than 0, then A is less than 0 and C is less than 0. So AC is going to be a negative times a negative, which is still positive. So A is related to C, and we are transitive. Great. This is an equivalence relation. That was part A of the proof. Let's see what part B was. So part B is determine the equivalence classes of tilde. So let's look at what the equivalence class of 1 is, because that should be easy. Well, 1 times any positive number is positive. So this equals positive R. It times the negative number is going to be negative, so those aren't related. And then let's look at the equivalence class of -1. Well, -1 times any negative number is going to be positive. So that's what it's related to. And all non-zero r is either positive r or negative r, so there's nothing left. Because we explicitly said in the problem statement that we weren't going to take 0 as a valid number in this problem. Okay. So, let's do number 6. Let A be the set of humans with English names. Define a relation double tilde on A by alpha is related to beta if A and B have the same first letter in their first names. Prove that this is an equivalence relation, and then determine the equivalence classes. Okay, so this isn't too bad either. Let's pull up paint.net. So, well, I guess reflexive isn't hard, and none of it's really all that hard, but reflexive is pretty easy. It's like every name has the same first letter as itself. That's reflexive. Symmetric, that if A has the same first letter as B, then B has the same first letter as A. Okay. And then transitive. If A and B have the same first letter and B and C have the same first letter, then A and C have the same first letter. So, transitive. And symmetric and reflexive. That gives us an equivalence class. And then, I'm betting that the second part was to show the equivalence classes. So, let's see. The equivalence classes, yes, determine the equivalence classes of double tilde. So that's not too bad. The equivalence classes are going to be, well, first letter A, B, C, X, Y, Z. So, I'm pretty sure that every letter has some name with it as the first letter. So, there's probably not an... So these would be the equivalence classes, because there's I'm sure that there's a name for every letter. If there were a letter that had no name, with that letter as the first letter, then that wouldn't be an equivalence class. It'd be the empty set. But anyway, those are the equivalence classes. So let's look back at our book. Let A be a set. Let R be a reflexive, symmetric, and antisymmetric relation on R. Prove that R is a quality on A. In other words, prove that for every X, Y, and A, X is related to Y if and only if X is Y. Okay, so reflexive, symmetric, antisymmetric. So, is reflexive, symmetric, and antisymmetric. We want to prove its equality. So, suppose x is related to y. By symmetry, y is related to x. By anti-symmetry, x equals y. So that proves like one direction, I guess. That proves that if they're related, then they're equal. And then the other way is like, suppose x equals y, then x is related to x by reflexivity, so x is related to y by substitution. Okay, so yeah, so x is congruent to y if and only if y is equal to x. And that's our proof. Okay, so that is the end of that section. So we will see you all on Thursday. So if you have questions, please email them to me. And we will do another section of the book on Thursday. See you. Bye.